Hi guys, Audrey here. Okay, so we've dealt with finding the general term of sequences. The other thing that we really care about when it comes to sequences is do they converge or diverge? In other words, when the n gets really big, like towards infinity, what's happening to the numbers in the sequence? Are they going to one specific number? Are they like oscillating, bouncing back and forth between more than one number? Or are they like going off to infinity or negative infinity? So we're going to start with this example. There were a few different things that we saw that could happen. To determine if a sequence converges or diverges, we just need to look at the limit. So the limit as n goes to infinity, 3n over the square root of n squared plus 1. So like I said, there are a number of things that we saw could happen when you're doing these limits that might make you think about them a little bit differently than limits that we were doing with L'Hopital's rule, for example. Okay, so the first thing we do with this is to plug in. And when I plug in, I get infinity over infinity. So that means that I'm allowed to use L'Hopital's rule. But one thing that we talked about is how if there is a square root, oftentimes L'Hopital's rule will send you in circles. Therefore, using L'Hopital's rule is probably not the best plan. So L'Hopital's rule will send you in circles. Probably. So what we're going to do instead is recognize that when I'm doing sequences, I'm always looking at the limit as n approaches infinity. 100% of the time, that limit is going to be going to infinity. So what that means in terms of like rational functions or functions like this, it means that I can just take the big stuff, take the dominant terms. So the big stuff here in the numerator is clearly 3n. In the denominator, you might think it's just n squared, but we actually have to take the square root with us. So that means here, this is the limit as n approaches infinity of 3n over the square root of n squared, which is just equal to the limit as n approaches infinity of 3n over n. The square root of n squared is just positive n. N is going to infinity. N is always a positive number, so it's just a positive n there. So that means we can cancel out those n's and get that this limit equals to 3. So my final answer here is that this converges to 3. Okay, so that's one of the first things that can happen. We could end up with like a square root or L'Hopital's rule. Sure, we're allowed to use it, but if I use it over and over and over again, I'm still just not going to get anywhere. So that would happen in this case. Okay, so our next sequence is n times n plus 3 factorial over n plus 2 factorial. In other words, we have a ratio of factorials. So if I'm doing the limit as n approaches infinity, n times n plus 3 factorial over n plus 2 factorial. Plugging in, well, n factorial, infinity factorial, that's like infinity times infinity minus 1, times infinity minus 2, times infinity minus 3. So it's like infinity times itself a bunch of times. So clearly that's just infinity. So I'm getting infinity over infinity. So once again, this is a situation in which it seems like I could use L'Hopital's rule. But factorials aren't functions. They don't make sense as functions. They're only defined for whole numbers, which means that I can't do L'Hopital's rule. Factorials don't have derivatives. So what we've seen to do instead is that we're going to identify what the bigger factorial is. In this case, the bigger factorial is n plus 3 factorial. So I'm going to take that bigger factorial and I'm going to expand it until I get to the smaller factorial. In this case, the smaller one is n plus 2. So n plus 3 minus 1, that gives me n plus 2, and I'm actually immediately there. So I'm going to replace that n plus 3 factorial with n plus 3 times n plus 2 factorial, and then cancel out those factorials. So when we have a ratio of factorials, our goal is always to get rid of the factorials. I just did that. So I'll get that this is the limit as n approaches infinity of n times n plus 3. And when I plug in infinity, I just get infinity. which means in this case, my final answer is that this diverges. So A sub n diverges in this case. The numbers just keep getting bigger and bigger forever. Okay, so our next example is a ratio of exponentials, 7 to the n plus 2 plus 5, all divided by 6 to the n plus 3. Okay, so again, I'm going to be looking at the limit as n approaches infinity of the sequence, 7 to the n plus 2 plus 5 over 6 to the n plus 3. And again, when I plug in, I'm going to get infinity over infinity. 7 to the power of infinity plus 2, that's like 7 to the power of infinity, which is like 7 times 7 times 7 times 7 times 7 times 7, an infinite number of times. So clearly that's becoming infinite. Same thing happening on the bottom, 6 times itself an infinite number of times. That's getting like extra super big, for sure. So again, it seems like maybe we could use L'Hopital's rule. But same as in the first question, L'Hopital's rule will send us around in circles here. Or not really circles, we could just keep doing it over and over and over and over and over again and never get anywhere. So when we have a ratio of exponentials, L'Hopital's rule will never get us anywhere. So instead, what we need to do is use our exponent rules. So we have an exponent rule that says that a to the b plus c is equal to a to the b times a to the c. I'm going to start off with that one, and I'm going to say that this is equal to the limit as n approaches infinity of 7 to the n times 7 squared plus 5 over 6 to the n times 6 cubed. Now my ultimate goal here is to use these exponent rules to get just one n left over. So right now I've still got those two n's. There's nothing I can really cancel out or combine because of this plus 5 here. That plus 5 is sort of stopping me from being able to combine things. So what I'm going to do now is separate this into two limits, or rather into two things. I'm going to distribute the denominator to each of the terms in the numerator to give me 7 to the n times 7 squared over 6 to the n times 6 cubed plus 5 over 6 to the n times 6 cubed. Well, now what I see here is that in the numerator I have something to the n, and in the denominator I have something to the n. So I was able to like separate that. So now I have 7 to the n and over 6 to the n. So the next exponent rule that I'm going to use is that a to the c over b to the c is equal to a over b to the c. If both things are to the same power, then I can pull that power out and have just one power. Or alternatively, how you might be used to thinking of it is if you have a over b to the c, then you can distribute that c to both the numerator and the denominator. So that's what I'm going to do in this case. I'm going to end up with the limit as n approaches infinity. I'm going to pull that 7 squared times 6 cubed to the outside, and then I will have 7 over 6 to the power of n, plus 5 over 6 to the power of n times 6 cubed. Now, what's happening here? When I plug in my n, I'm looking at 7 over 6 to the power of n. 7 over 6 is a number that's bigger than 1. So when I do 7 over 6 times 7 over 6 times 7 over 6, when I put it to the power of infinity and do it times itself an infinite number of times, what's going to happen is that it's just going to get bigger and bigger and bigger. So this right here is going to infinity plus 5 over 6 is also going to give me infinity when I put it to the power of infinity. So this is just like infinity plus 0. Remember, division by infinity gives 0. So this is just infinite. So again, my answer here is that a sub n diverges. Final answer. So We talked about the limit of r to the power of n when we have a number to the power of n, and we saw that it can take on lots and lots and lots of different values. So I'm just going to remind you of that really quickly. So we'll see why 6 to the n and 7 over 6 to the n both give infinity. So the limit as n approaches infinity of r to the power of n goes to infinity if r is bigger than 1, because numbers that are bigger than 1 multiplied by themselves become bigger. So r times r times r times r times r is getting bigger if it's bigger than 1. However, it goes to 0 if -1 is less than r is less than 1. And the reason for that is because, let's say that I have a half. A half times a half gives me a fourth, which is smaller than a half. Times a half gives me an eighth. So as I multiply a half by itself over and over and over again, instead of getting big, it's getting smaller and smaller and smaller. So if r is between -1 and 1, I just realized I didn't actually write the 1 there. If r is between -1 and 1, then the values are getting smaller. And so that's going to 0. Then if r equals 1, well, that's just like 1 times itself over and over again. So that's just going to give me a 1. And then the last option is that it possibly doesn't exist if r is less than or equal to -1. And the reason that it would not exist is because if it's less than or equal to -1, then it's a negative number. Negative numbers to even powers are positive. Negative numbers to odd powers are negative. So as n is on the way to infinity, it's going to be going back and forth between even and odd numbers, and therefore going back and forth between positive and negative numbers. So it's going to be bouncing back and forth between positive and negative. It's going to be oscillating, which means that that limit will not exist. Okay, so that's why our 7 over 6 there is going to infinity, and why this thing diverges. Okay, we saw a ratio of factorials, we saw a ratio of exponentials, we saw a square root that would cause us to go around in circles. Here's one last thing that I want us to talk about here. And that one last thing is a difference of indeterminate forms. Another thing that shows up in this problem is the fact that there is this -1 to the n right here. That -1 to the n means that this is alternating. Now that's important for making our conclusion and for telling us how we're going to go about the problem. What we know is that alternating sequences can only converge to 0. They can't converge to 1 or -1 or 5 or -5. They would be bouncing back and forth between positive and negative numbers. So they can only converge to 0. That's the first thing we know. The second thing we know is that if a series is alternating, we can ignore the alternating part when we're doing the limit. So I can ignore the -1 to the n to just see the value that I get. And after we have the limit, we'll just talk briefly about why we can ignore it. So let's look at the limit then. As n approaches infinity, ignore the -1 to the n, 3n over n plus 2, minus 6n minus 4 over n. This first thing gives me infinity over infinity when I plug in, and the second thing gives me infinity over infinity when I plug in. So I want to look at each of these limits separately. So we'll call this first one a smiley face, and we'll call this second one a frowny face, and just look at each of them separately. So if I'm looking at smiley face, I'm just looking at the limit as n approaches infinity of 3n over n plus 2. That's my infinity over infinity. I'm going to use L'Hopital's rule for this one, and we're going to do the other one using a different method. So infinity over infinity means L'Hopital's rule is allowed. So this is the limit as n approaches infinity. The derivative of 3n is 3. The derivative of n is 1. And I get that the answer to this part is 3. So for frowny face, we'll have the limit. Oops, that's the wrong pin. We'll have the limit as n approaches infinity of 6n minus 4 over n. Again, I get that infinity over infinity. I could use L'Hopital's rule if I wanted, but I can also just take the dominant terms. Here I'm using L'Hopital's rule, here I'm taking the big stuff. To see that this is the same thing as the limit as n approaches infinity of 6n over n, those n's cancel out, and I get that this is just equal to 6, which tells me then that my original limit, 3n over n plus 2 minus 6n minus 4 over n, is equal to 3 minus 6, which is negative 3. Now, what does that negative 3 tell me? It tells me that the original sequence is therefore approaching numbers that are bouncing back and forth between 3 and negative 3. So bouncing back and forth between numbers approaching 3 which brings us to the first thing that we remembered. Alternating sequences can only converge to 0. That negative 3 does not equal to 0. So because this is alternating, it diverges. It diverges because it's bouncing back and forth between those positive and negative numbers. All right, so those are like the main types of things that can happen in sequences that would stop us from using L'Hopital's rule, or where we have to think about them in a little bit of a different way. That's all. Bye, guys.